Hi, and welcome to the Zynq 7000 System on Chip Highlights video. My name is Majid, and I will walk you through this presentation. In this video, our aim is to provide the solid foundation of the Zynq architecture. We will start by introducing the Zynq 7000 System on Chip, then we will give an overview of the Zynq 7000 and the ZedBoard, and present a simplified model of the Zynq architecture. We will then review the key elements of the Zynq in more details, starting with the processing system, which will cover the A.P.U, Neon engine, and the processing system external interfaces. We will then discuss the programming logic, which consists of the logic fiber, general purpose I.O., communication interfaces, and other programmable logic external interfaces. The AXI will then be briefly introduced to give an idea of how the processing system and programming logic communicates. We will then proceed to present the application area of Zynq and lastly, give a family overview of Xilinx. The Zynq combines a dual-core ARM processor with a traditional field programmable gate array logic fabric. The concept of combining ARM with FPGA has been around for a while, and the goal is that a single silicon chip can be used to implement the functionality of an entire system rather than several different physical chips being required. And this is the concept of the system on chip as shown in the image to the left of the slide. Instead of having all the required functions in physically separate devices, the SoC combines all of them in a single device. This combination has proved to be flexible and forms a compelling platform for a wide variety of applications that will be discussed. In fact, there are a number of compelling reasons for preferring SoCs over discrete component equivalent systems. The SoC solution enables faster and more secure data transfers between the various system elements, has higher overall system speed, lower power consumption, smaller physical size, better reliability, and lower costs. The ARM function is to provide an application-grade processor capable of running full operating systems such as Linux. The FPGA is based on Xilinx 7 series architecture and provides a flexible device that can be configured to implement any arbitrary system, including embedded processors if needed. FPGAs has three key importance in the Zynq architecture: fast time to market, flexibility, and the ability to upgrade. The architecture is completed by industry-standard AXI interfaces which provide high bandwidth, low latency connections between two parts of the device. This is the overall view of a ZedBoard. The Zynq device is highlighted in yellow. The ZedBoard is a complete development kit for designers interested in exploring designs using the Xilinx Zynq-7000 all-programmable SoC. The board contains all the necessary interfaces and supporting functions to enable a wide range of applications. There are several other types of boards that are compatible with the Zynq-7000 SoC series that makes it even more attracting for a wider pool of application. For this presentation, we will focus on the Zynq architecture. The Zynq 7000 family is based on all Xilinx programmable SoC architecture. These products integrate a single-core ARM Cortex-A9 based processing system, which will be referred to as PS, and 28nm Xilinx programmable logic, which will be referred to as PL in a single device. The ARM Cortex-A9 CPU further includes an on-chip memory, external interfaces, and a rich set of peripheral connectivity interfaces. In the next slide, we will peel the cover of the Zynq chip to see what's inside. This is a simplified model of the Zynq architecture, or in other words, under the hood of the chip. The Zynq comprises of two main parts as mentioned earlier, the ARM A9 and the FPGA. The processing system PS is formed around a dual-core ARM Cortex-A9 processor, and programmable logic PL is equivalent to that of an FPGA. The PL section is ideal for implementing high-speed logic arithmetic and data flow subsystems, while the PS supports software routines and operating systems, meaning that the overall functionality of any design system can be appropriately partitioned between hardware and software. The links between the PL and PS are made using industry-standard Advanced Extensible Interface AXI connections. Communication between system elements take place via interconnections. These may be in the style of direct, point-to-point links, or buses serving multiple components. Peripherals are functional components residing away from the processor, and in general, these perform one of three functions. Coprocessors are elements that supplement the primary processor, usually optimized for a certain task. cores for interacting with external interfaces, example connecting to LEDs and switches, or could be additional memory elements. The PS has a fixed architecture and hosts the processor and system memory, whereas the PL is completely flexible, giving the designer a blank canvas to create custom peripherals or to use standard ones. It is important to know that the Zynq is an SoC, which means a wide variety of standard intellectual property, also known as IP, is available. This means that there is no need to redesign these components. The PS and PL can be used independently or together, and in fact, the power circuitry is configured with separate domains enabling either the PS or PL to be powered down if not in use. On the lower left side of the Zynq architecture, we can notice an optional microblaze processor. The microblaze role is to coordinate specific low-level functions within the system, less demanding tasks, which can be delegated away from the main ARM Cortex-A9 processors to enhance overall performance. Now we will introduce the PS and PL individually and understand each of their tasks, characteristics, and properties. Let's start with the PS, the processing system. Earlier, we briefly introduced the Zynq device as a combination of ARM A9 processor and the Xilinx FPGA at a simplified high-detail view. Now it is important to note that the PS does not consist only of the ARM processor, but also a set of associated processing resources forming an application processing unit A.P.U, which consists of peripheral interfaces, cache memory, memory interfaces, interconnect, and clock generation circuitry. So let's start with the A.P.U. The A.P.U consists of a dual-core ARM Cortex-A9 processor, which has a speed of up to 1 GHz, Neon Media Processing Engine, MPE, Floating Point Unit (FPU), Memory Management Unit (MMU), Level 1 Cache Memory, which has a size of 32 kilobytes, which permits local storage of frequently required data and instructions for fast access times and optimal processor performance. Level 2 Cache Memory, which is 512 kilobytes in size and is used for sharing instructions and data. An on-chip memory OCM, which is 256 kilobytes in size and is used to translate virtual and physical addresses. A Snoop Control Unit, which is referred to as SCU, which forms a bridge between the ARM cores and the Level 2 cache and OCM memories and some interfacing with the PL. Let's discuss the Snoop Control Unit in more detail. The Snoop Control Unit is one of the several mechanisms for ensuring cache coherency, which is the managing of consistency of data across shared cache resources. The SCU is responsible for maintaining memory coherency between the processor data cache memories, which are marked as L1D, and the shared Level 2 cache memory. It also initiates and controls access to the Level 2 cache, arbitrating between requests from the two cores where necessary. The SCU additionally manages transactions that take place between the PS and PL via the Accelerator Coherency Port (ACP), not shown in the simplified A.P.U diagram. Let's take a more detailed look of the Neon and the floating point extensions. Neon Engine provides a single instruction multiple data, also referred as SIMD, which facilitates and enables the strategic accelerations of media and DSP type algorithms. The Neon engine can accept multiple sets of input vectors upon which the same operation is performed simultaneously to provide the corresponding set of output vectors. This style of computation caters well to applications like image and video processing, which operate on a large number of data samples simultaneously, and inherently parallel generic signal processing functions such as finite impulse response filters and fast Fourier transforms. In the figure shown, there are two input registers, A and B, each of which contain a set of n individual input vectors. A single defined operation is performed between the n sets of input vectors to produce a corresponding set of output vectors which are written to the output register. The size of the vectors can vary, as can the number of vectors comprising each register. The important feature is that each lane produces results arising from the same operation, which is performed on several different sets of inputs at the same time. Hence the term single instruction multiple data. Neon supports a variety of data types including signed and unsigned integers, single precision floating point, and half precision floating point. Let's talk about the second part of the processing system, PS, the external interfaces. Communication between the PS and external interfaces is achieved primarily via the multiplexed input-output EMIO. It provides 54 pins of flexible connectivity, meaning that the mapping between peripherals and the pins can be defined as required. The available I/O includes standard communication interfaces and general-purpose input-output, which can be used for a variety of purposes, including simple buttons, switches, and LEDs. The SPI serial peripheral interface is a serial communication based on a 4-pin interface. It can be used in the master mode or the slave mode. The I2 bus is based on I2 bus specification and supports also the master and slave mode. The CAN, also known as the Controller Area Network, is in compliance with the ISO 118981 and supports the 2.0A standard and the 2.0B standard. The Universal Asynchronous Receiver Transmitter has a low-rate data modem interface for cellular communication and is often used for terminal connections to a host PC. The general-purpose input-output has 4 banks of GPIO, each of 32 bits. The SD is used for SD card memory. The USB is used for Universal Serial Bus and is in compliance with USB 2.0 and can be used as a host, device, or flexibility. The Ethernet MAC peripheral supports up to 10 megabytes, 100 megabytes, and 1 gigabytes. Programmable logic is based on the FPGA fabric. Now that we have thoroughly covered the PS processing system part, which was the ARM A9 Cortex processor located, let's talk about the PL. The PL is predominantly composed of general-purpose FPGA logic fabric, which is further composed of slices and configurable logic blocks, CLBs. The PL has 2 special resources known as DSP48E1S and block ROMs. Finally, the PL consists of general-purpose input-output to allow communication with the outer world. Now let's describe each part to understand the logic fabric. Configurable logic blocks, CLB, are small, regular groupings of logic elements that are laid out in 2-dimensional array on the PL and connected to other similar resources via programmable interconnects. Each CLB is positioned next to a switch matrix and contains 2 logic slices. But what is a slice? A slice is a subunit within the CLB, which contains resources for implementing combination and sequential logical circuits. Zynq slices are composed of 4 lookup tables, 8 flip-flops, and other logics. The lookup table LUT is a flexible resource capable of implementing a logic function of up to 6 inputs, a small read-only memory, a small random access memory, or even a shift register. LUTs can be combined together to form larger logic functions, memories, or shift registers as required. The flip-flop is a sequential circuit element implementing a 1-bit register with reset functionality. One of the FFs can optionally be used to implement a latch. A switch matrix next to each CLB provides a flexible routing facility for making connections, firstly between elements within a CLB or from one CLB to other resource on the PL. The carry logic is an arithmetic circuit that requires intermediate signals to be propagated between adjacent slices, and this is achieved via carry logic. The carry logic comprises a chain of routes and multiplexers to link slices in a vertical column. The input-output blocks are resources that provide interfacing between the PL logic resources and the physical device pads used to connect to external circuitry. Each IOB can handle 1-bit input or output signal. IOBs are usually located around the perimeter of the device. There are 2 special purpose components, block RAMs for dense memory requirements and DSP48E1 slices for high-speed arithmetic. The block ROMs can implement random access memory, read-only memory, and first-in first-out buffers while also supporting error-correct encoding. Using a block RAM means that a large amount of data can be stored in a physical, small size on a device within a dedicated and optimized memory element. The DSP48E1 makes use of multiplexing circuitry to permit flexible usage of registers and to support dynamic alteration of the computation. Various computations are possible involving 1, 2, or 3 arithmetic operators. It is also capable of SIMD processing, implementing 2 or 4 shorter addition, subtraction, accumulation operations of 24 or 12 bits respectively. When used in logic mode, it can perform logical functions instead of arithmetic and supports all of the fundamental Boolean operations, bitwise, NOT, AND, OR, NAND, NOR, XOR, and XNOR. As a result of these properties, DSP48E1 is situated to a variety of applications in signal processing and beyond. The general-purpose input-output are collectively referred to as the select I/O resources, and these are organized into banks of 50 IOVs each. Each IOV contains one pad which provides the physical connection to the outside world for a single output or a single input. The I/O banks are categorized as high-performance HP or high-range, and these support a variety of I/O standards and voltages as detailed. The HP interfaces are limited to voltages of 1.8 volt and are typically used for high-speed interfaces to memory and other chips, while the HR interfaces permit voltage of up to 3.3 volt and cater for a wide variety of I/O standards. Both single-ended and differential signal are supported, requiring one IOV and two IOVs per connections respectively. Communication interfaces is a highly specified Zynq device and usually include a GTX transceiver, high-speed communication interface blocks which are embedded into the logic fabric. These are dedicated silicon blocks and are capable of supporting a number of standard interfaces including the PCI Express, the Serial Rapid I/O, SCSI, and SATA. The interfaces can be used to create connections to independent external devices such as networking equipment, hard disk, and further FPGA or devices. Other programmable logic external interfaces are the analog to digital conversion. The PL includes another hard A.P.U component, the XADC block. This is a dedicated set of analog to digital converter mixed signal hardware which features two separate 12-bit ADC, both capable of sampling external analog input signals at 1 MSPS. Control of the XADCA is achieved using the PS-XADC interface block located within the PS, and the PS-XADC, which is the processing system analog to digital converter control block, can itself be programmed from the software executing on the A.P.U. The clock. The PL receives 4 separate clock inputs from the PS, and additionally has the facility to generate and distribute its own clock signals independently of the PS. The independent PL resources are equivalent to those of a 7 series FPGA. Programming and debug. A set of GTAC ports are provided in the PL section to facilitate configuration and debugging of the PL. Although more secure methods are normally preferred in the deployment, GTAC configuration is often used during the development phase. This facilitates overt via GTAC supports debugging with both ARM and Xilinx tools. The AXI standard. In this section, we will examine the connections between the PS and PL and consider how they can be used. We begin by introducing the AXI standard upon which of most of these connections are based. AXI stands for Advanced Extensible Interface, and the current version is AXI4, which is part of the ARM AMBA 3.0 open standard. The AMBA standard is now described by ARM as the de facto standard for on-chip communication. AXI buses can be used flexibly and in general sense are used to control the processors and other IP blocks in an embedded system. In fact, there are 3 flavors of AXI4, each of represents a different bus protocol and as summarized below. The choice of AXI bus protocol for a particular connection depends on the desired properties of that connection. AXI4 is used for memory mapped links and provides the highest performance, and address is supplied followed by a data burst of up to 256 data words. AXI4 Lite, a simplified link supporting only one data transfer per connection. AXI4 Lite is also memory mapped. In this case, an address and single data words are transferred. AXI Stream is used for high-speed streaming data, supporting burst transfers of unrestricted size. There is no address mechanism. This bus type is best suited to direct data flow between the source and destinations of non-memory mapped links. The AXI interconnects and interfaces. The primary interface between the PS and PL is via a set of 9 AXI interfaces, each of which is composed of multiple channels. These make dedicated connections between the PL and interconnects within the PS. It is useful to briefly define these 2 important terms. Interconnect. An interconnect is effectively a switch which manages and directs traffic between attached AXI interfaces. There are several interconnects within the PS, some which are directly interfaced to the PL, and others which are for external users only. The connections between these interconnects are also formed using AXI interfaces. An interface is a point-to-point connection for passing data, addresses, and handshaking signals between master and slave clients within the system. The general-purpose AXI is a 32-bit data bus which is suitable for low and medium-rate communications between the PL and the PS. The interface is direct and does not include buffering. There are 4 general-purpose interfaces in total. The PS is the master of two, and the PL is the master of the other two. Accelerator coherency port is a single asynchronous connection between the PL and the SCU within the APU, with a bus width of 64 bits. This port is used to achieve coherency between the APU caches and elements within the PL. The PL is the master. High-performance ports. There are 4 high-performance AXI interfaces, include FIFO buffers to accommodate bursty read and write behavior, and supports high-rate communications between the PL and memory elements and the PS. The data width is either 32 or 64 bits, and the PL is the master of all 4 interfaces. EMIO interfaces. As mentioned in earlier sections, several connections from the PS can be routed through the PL to external interfaces, and this can be done by the extended EMIO or EMIO. EMIO involves a signal transfer between the two domains and is achieved through a simple set of wire connections. Consequently, not all EMIO interfaces are supported in EMIO, and some of those which are supported have reduced capabilities. The connections are arranged in two 32-bit banks. Interfaces routed through the EMIO are in many cases connected directly to the desired external pins of the PL, as specified by the inclusion of the appropriate entries in a constraints file. In this mode, EMIO can provide an additional 64 inputs and 64 outputs with corresponding output enables. Another option is to use EMIO to interface the PS with a peripheral block in the PL. The figure to the left dissipates both of these models. Application areas of Zynq. Now that we have covered the Zynq architecture and highlighted the key components and characteristics of the processor, let's survey the general landscape of applicable products and systems that the Zynq can be used for. The Zynq processor can be used in automotive, military, aerospace, image processing, wired and wireless communications, medicine, industrial control, and many other examples. The main reason that Zynq can be used in a wide range of products is because the Zynq architecture can be leveraged to meet the demands of applications with significant requirements in terms of both high performance, computational, and sequential processor-intensive functionality. Let's look at the Zynq-7000 family portfolio overview. First thing to be pointed out is that all the Zynq-7000 devices share the same processing system, memory controller, peripheral, and interface to the programmable logic. The intention here is to offer a common base platform that will allow designers to migrate their design from one device to another. The differences is the programming logic, which scales more or less customization depending on the target application. As you choose higher-end Zynq devices, you get more embedded memory and more DSP blocks. You also get more I/O to connect external devices. This presentation has reviewed the general architecture of the Zynq device and detailed its two component parts, the PS and the PL, together with the resources for interfacing between them. The processing system was shown to include a dual-core ARM Cortex-A9 processor with associated extensions for SIMD and floating point processing grouped together in an A.P.U unit along with memory resources. The capabilities of the A.P.U and its interfacing to the rest of the processing systems were highlighted. The internal structure of the PS as a whole and its connection with the programmable logic was also explained. The structure and resource of the programmable logic section was outlined, including the fabric logic, block RAM, and DSP48E1 resources and interfacing resources, and the important issue of interfacing between the PL and PS using AXI was also reviewed. Lastly, a comparison was made between the device members of the Zynq-7000 family. Thank you for watching this video.